In our previous lesson, we learned how to use DeMoivre's theorem to calculate the exponents of a complex number. Now we're going to do a small modification to DeMoivre's theorem to be able to use it to calculate fractional exponents of complex numbers. With that in mind, this is knowledge that we can use to solve equations of the form z power n equals some complex number. And for polynomials that have non-zero coefficients in the other powers of z, we are going to incorporate different method. We're going to do long division, and we're going to talk about the factor and remainder theorems. So that's going to come in the second part of this lesson. So let's begin with equations of the form z power n equals to a. Let's begin by defining what our number z and our number a are going to be. So z in cis form, let's make it p cis of alpha, and a, let's make it r cis of theta. Z power n is going to be then, if we use the DeMoivre's theorem, z power n is going to be p power n cis of n alpha. So what we get is that since z power n is equal to a, we get p power n cis of n alpha is going to be equal to r cis theta. Now let's remember that these are two different complex numbers, and the only way they can be equal is if their arguments are matching and if their modulus are the same. So we can say that p power n has to be equal to r. This is the first outcome that we get. And so what we get from here is that p is going to be the nth root of r, or r to the power of 1 over n. These are the same thing, the nth root of r, or r to the power of 1 over n. Now the second thing that we mentioned is that their arguments need to match. Now what that means is that if my number a has a modulus theta right here, then the modulus of z power n, or n alpha, has to match that same end point. So it has to cover this angle as well. But the thing is, it has to cover that much, but it doesn't necessarily mean that it has to be the same number of cycles. N alpha can be a full cycle plus that angle, or it could be 2 cycles plus that angle. So what that means for the arguments is that n alpha is going to be theta plus a number of cycles. So it's going to be theta plus 2k pi, where 2 pi times k is representing the additional cycles. Now when we do this, the result that we see is that then the angle alpha is going to be theta plus 2k pi divided by n. So when we build the number z with these two parts of information, we are getting that z is going to be in cis form, is going to be r to the power of 1 over n, remember that is p, times cis of the argument, which is alpha, and alpha is theta plus 2k pi over n. Now let's think about which values of k can I use to find the values of z. I am going to have in this equation z to the power of n equals to a, I'm going to have n different solutions. So I need to make sure I change the value of k n times in order to get a different solution from each of the values of k. So what I'm going to do is I'm going to take the argument, so theta plus 2k pi over n, and I'm going to distribute the n to write it as two separate fractions like this. So what I see here is if k starts at 0, then this term is going to be 0 and the angle is going to be theta over n. Now if k is equal to n, then k over n would cancel. I would get simply 2 pi, and I would have theta over n plus 2 pi, which is essentially the same angle as theta over n. So that is already telling me that this solution when k is equal to n is a repeated solution, or is giving me one solution that I already found when the value of k was 0. So there is no point in continuing to take different values of k above n minus 1. So I'm going to limit the values of k from 0, 1, 2, 3, etc. But the last one I'm going to take is n minus 1. Now with this limitation, we make sure we have n solutions of the equation of degree n. Let's do an example to see this in action. For our first example, let's solve the equation z power 3 equals to 1. So in this case, the number a is going to be 1, and we need to write it in cis form. 1 in cis form is 1 cis of, it can be 0 or it can be 2 pi. I'm choosing 0. Now what I want is to find z, which would be the solution. So according to the rule that we discovered last time, z is going to be 1 to the power of a third cis of 0 plus 2k pi divided by 3, where k is going to take values 0, 1, and 2. So we're going to find the first value of z when k is 0. So that is going to be 1 cis of 0 over 3, that is equal to 1. The second value of z is going to be 1 cis of 0 plus k is equal to 1, so 2 pi over 3. That is the same as 1 cis of 2 pi by 3. And the third value of z is going to be 1 cis of 0 plus k is equal to 2. So it's going to be 4 pi by 3. And that is the same as 1 cis of 4 pi by 3. Or another way of writing this would be 1 cis of minus 2 pi by 3 if we use the principal argument. Now notice here one thing. We have 3 solutions. Because the power is 3, it's an odd power. One of the solutions is real. It's not paired with anything. It's real. It's 1. The other 2 solutions are complex numbers. Furthermore, they are complex numbers that are complex conjugates. Notice how the second root, cis of 2 pi by 3, and the third root, cis of minus 2 pi by 3, are complex conjugates. So this is going to be a property that you're going to be seeing in every equation of this kind. The roots of polynomials are going to come always by complex pairs. Any root that is a complex number will have its conjugate also as a root of the polynomial. So once you find one root, you don't really have to find the other one by doing the process. You can just assume that its complex conjugate is going to be present as a solution as well. If we look at the position of these 3 solutions of the equation that was given in the complex plane, then we're going to notice something special about these solutions. The first solution is 1, and that is located on the real axis. Then the second solution is cis of 2 pi by 3. 2 pi by 3 is 120 degrees, so it should be somewhere around here. And the third solution is minus 2 pi by 3, so it should be somewhere in this area. Now, the three solutions are in a unit circle because the magnitude of the number is 1. And just having the circle, it helps us visualize this pattern. So if we draw the 3 radii from the circle, we can tell that the distance in terms of angle, so the angular distance between these 3 points, is going to be 120 degrees, or 2 pi by 3. So what we can say is that these 3 solutions are forming, or are the vertices of, a regular triangle, so an equilateral triangle. This is another property that we're going to find in the solutions of an equation like this one. The solutions are always going to form the vertices of a regular polygon of n sides. In this case, we have n is equal to 3. The power of z is 3. So we should get 3 solutions. That means we should have our solutions forming an equilateral triangle. For our second example, we're going to find the 8 roots of minus I. So to start, we need to write minus I in cis form. And the equation that we're going to solve is going to be z power 8 equals minus I. So minus I in cis form is going to be cis of minus pi by 2, or if you prefer, cis of 3 pi by 2. So we're going to use this form. Now what we want to do is we want to use this solution that we created for the solutions of this equation. So what we're going to do next is we're going to say Z1 is going to be, the modulus of this is still 1, so this should be 1 cis of 3 pi by 2 plus 0 divided by 8. Z2 is 1 cis of 3 pi by 2 plus 2 pi divided by 8. Z3 is 1 cis of 3 pi by 2 plus 4 pi divided by 8. Z4 is 1 cis of 3 pi by 2 plus 6 pi divided by 8. And before we find the other 4 solutions, because in this case we should find 8 solutions, let's simplify these ones. So this is going to be cis of 3 pi by 16. Z2 is going to be cis of 7 pi by 16. Z3 is going to be cis of 11 pi by 16. Z4 is going to be cis of 15 pi by 16. Now similarly we can do the other 4 roots. And so we have found all the 8 roots of minus I.